Welcome everyone to today's deep dive. I'm incredibly excited because today we are embarking on something of well, a massive intellectual expedition.
Absolutely massive.
Right. We are going to take the purest, most intimidating mathematical formulas of artificial intelligence, and we're going to break them down.
Break them down into an absolute masterclass.
Exactly. A masterclass on how to make the ultimate decisions in a completely chaotic universe.
Which is what we all want, right?
Right. So imagine you have this stack of incredibly dense academic papers sitting right in front of you. Specifically, we are unpacking a fascinating, highly technical analytical report. It's titled Computational Cybernetics and Strategy Optimization Logic Mapping in Non-Stationary Environments.
Quite the mouthful.
It really is. Now, if you are familiar with the field, you know this is fundamentally rooted in the second edition of the seminal textbook on reinforcement learning.
The Bible of the field, basically.
Yeah, but if that title alone makes you want to, run for the hills, please do not worry. That is exactly why we are here today.
We are going to translate all of that Greek alphabet soup
Into something you can actually use. Something that will help you understand how intelligence, both artificial and your own human cognition, actually works at a mechanical level.
It is a profound topic, and it's wonderful to be here diving into it with you because what we are really talking about when we look at this foundational source material is the ontology of algorithms.
The ontology.
Right, the fundamental nature of being. We are not just looking at computer code, we are looking at perceiving and deciding. The literature doesn't just give us programming syntax.
It gives us the axioms.
The absolute axioms of learning. It asks a universally applicable question. How does any entity at all, navigate a world it doesn't fully understand?
To achieve a specific goal.
Exactly. Whether that entity is a rover on Mars or a high-frequency trading algorithm or, a human being just trying to navigate a complex social hierarchy.
The underlying mathematics of that struggle are shockingly identical.
They really are.
Okay, let's unpack this. The material starts by setting the absolute baseline of this entire universe. It talks about Markov decision processes, or MDPs.
The bedrock.
Right. And the core logic here is fascinating to me, but also a bit jarring. It says we need to strip away all the messy physical complexity of reality.
All of it.
Like, you don't need to know the atmospheric pressure on Mars. You don't need the exact emotional state of the people in the grocery store. It reduces all interaction between an entity and its environment into a pure math graph.
A discrete time series of probabilities.
Yes, but how does that reduction actually work? How do we take the infinite complexity of the real world and squash it into an equation without losing the essence of what it means to make a decision?
That reduction is the genius of the entire framework, and it's something the pioneers of optimal control theory debated for decades.
I can imagine.
It is the first principle from which all modern artificial intelligence decision-making flows. In the source material, this is formalized in a concept they call the complete representation of environment dynamics. Now, the actual formula they use is highly compressed. It's essentially a four-part mathematical engine of cause and effect.
Let's break down the geometry of that engine conceptually for the listener, because it is the absolute bedrock of everything we're going to discuss today.
Right. Imagine a boundary line. On one side of the line, you have the internal world of the agent.
The brain.
The brain, the code, the mind. On the other side, you have the external universe.
Okay, I'm picturing it.
First, you have your state. The variables this is your current situation. The exact quantifiable configuration of your world at this precise millisecond.
Got it.
Then you have your action. The variable A. This is your agency. The control variable you can manipulate. You decide to exert force on the world.
Right, so to put myself in the shoes of the algorithm here, I am currently in a specific state, and I choose to take a specific action. Like, I am standing in a kitchen, that's my state.
Yes.
And I decide to turn the knob on the stove. That's my action.
Exactly. And the millisecond you take that action, you cross that boundary line we talked about, the universe responds.
The environment pushes back.
It pushes back against your agency. That pushback results in the two variables on the other side of the equation's probability bar, the new state you find yourself in.
The burner is now on and hot.
Right, and the reward you receive for that transition.
Maybe I cooked an egg, so I get a positive reward.
Or maybe I burned my hand.
Exactly, a massive negative reward. So this dynamic engine is simply asking a universal question. What is the mathematical probability that I will end up in a highly specific new state and get a highly specific reward signal, given that I am currently in this exact state and I choose to take this exact action?
It's purely statistical.
It is a universal statistical mapping of cause and effect. It strips away the why of physics.
And just observes the what of probability. That makes sense. And the text heavily emphasizes something called the Markov property regarding that state variable.
Crucial concept. The idea that the system believes the current state is I think the term is sufficient statistic of all history.
Yes, a sufficient statistic.
If I'm understanding this correctly, it means the system has total, absolute amnesia about the past.
Practically speaking, yes.
But how can amnesia possibly be a good thing for an intelligence trying to learn?
What's fascinating here is that the Markov property isn't about forgetting out of weakness. It is about discarding out of ultimate efficiency.
Okay.
The property asserts that the present moment contains all the necessary information to perfectly predict the future. You do not need to know the exhaustive, sprawling history of how you arrived at your current state.
So the baggage doesn't matter.
Right. If you know the exact, complete, microscopic details of your state right now, the historical trajectory that brought you there provides absolutely zero additional predictive power.
It's just mathematically irrelevant noise.
Exactly. Think of classical mechanics. If you know the exact position and momentum of a ball flying through the air,
You don't need to know who threw it.
or how long it has been in the air, you can calculate exactly where it will land with just the current variables.
I love thinking about this, like navigating life as a complex board game.
Oh, that's a good way to look at it.
Think about chess. If you, as a player, walk up to a chess game already in progress, the clock is ticking, it's your turn, all you need to look at is the current physical position of the pieces on the board.
That is your current state.
Right. It absolutely does not matter if the previous player moved their knight 3 times in a circle before putting it on that specific square.
Or if they took 2 hours to make their last move.
Exactly.
Oh,
The history of the emotional struggle of the previous moves has no bearing on what your optimal next mathematical move should be.
zero bearing.
The current board state is the sufficient statistic. It contains everything.
That is a perfect analogy. The physical reality of the board right now is all that dictates the geometric probability of your success. And that brings us to the ultimate goal of the system.
Which the text defines as the reward hypothesis.
Yes. This is the philosophical core of reinforcement learning. And frankly, it's a statement that borders on the existential.
How so?
The hypothesis states that all goals, all purposes, all desires of an intelligent agent can be well thought of as the maximization of the expected value of the cumulative sum of a received scalar signal.
That is a very dense sentence.
Let's unpack it, meaning everything you want to achieve, whether it's winning a war, curing a disease, or just standing upright, can be mathematically boiled down to maximizing a single, simple number over the axis of time.
But it's not just about getting the biggest number right this second, right?
No, not at all.
Because the text provides a framework for how this cumulative signal is calculated over time. It calculates the total ultimate payoff. But it introduces this concept of discounting future rewards.
The gamma parameter.
Right. There is a specific mathematical weight attached to the future that diminishes it. Why does an artificial immortal math equation need to care about discounting the future?
It needs to care because the future is inherently uncertain, and computation is not free. This discount factor is a parameter that defines the system's entire perception of time and value.
How does that look in practice?
Well, if we set this factor to exactly 0, the system becomes completely myopic. It only cares about the immediate reward right in front of its face and ignores the future entirely.
Like a pure reflex arc. Touch a hot stove, pull your hand back.
Exactly. But if we set this factor very close to 1, the system develops profound, almost godlike foresight. A reward 100 steps in the future is almost as valuable to it as a reward today.
So why not just set it to exactly 1, give it perfect foresight?
Because setting it to exactly 1 in an infinite time frame causes the math to shatter. The sum of infinite rewards is infinity, and you cannot optimize for infinity. So you must discount.
That sounds exactly like business economics.
It really is.
When a company is doing corporate financial modeling, they use a discount rate for future cash flows. $100 in my hand today is objectively worth more to me than a legally binding guarantee of $100 10 years from now.
Because of inflation.
Inflation,
Yeah.
the opportunity cost of what I could have invested that $100 into today, and the sheer unavoidable entropy and uncertainty of the future. The company might go bankrupt in 10 years. The currency might collapse.
Right.
This mathematical discount factor is basically the AI's version of the time value of money, or the time value of existence.
I love that. The time value of existence, if we connect this to the bigger picture, it fundamentally mirrors how humans subconsciously operate every single day.
We're doing this all the time.
We are biological reinforcement learning agents, constantly weighing immediate gratification against long-term goals. Do you eat the entire box of cookies right now for a massive, immediate positive reward signal?
I usually do.
We all do sometimes. Or do you abstain because you have a long-term goal of running a marathon next year, which carries a highly discounted, heavily delayed reward in the distant future?
So the framework of the Markov decision process isn't just a sterile way to program a robotic arm on an assembly line.
Not at all. It is a mathematical mirror reflecting the universal psychological struggle of decision-making.
And the system's only mission, its only reason for existing, is to find a policy.
A perfect mapping of every possible state to the best possible action.
That maximizes that total discounted return over its lifespan. Okay, so what does this all mean when you drop an intelligence into a world and it doesn't actually know the rules of the game?
That's where it gets complicated.
We've talked about the baseline, but let's transition into the deep end of uncertainty. The text explores a classic dilemma known as the multi-armed bandit problem.
A classic.
You're in an environment, you desperately want to maximize your reward, but you have absolutely no idea what your actions will actually do. You are blind.
This is where we encounter the fundamental mathematical tension of all sentient life.
That sounds intense.
It is. It's the eternal war between curiosity and greed. In a multi-armed bandit scenario, which is whimsically named after a gambler facing a long row of slot machines in a casino.
Where each machine has a completely unknown payout probability.
Exactly. The agent has to figure out which machine is the most lucrative. Let's say you pull the lever on the first machine a few times, and it pays out reasonably well. It gives you a steady drip of coins.
Your immediate mathematical instinct might be to lock in.
Right. Just keep pulling that exact lever forever. In algorithmic terms, this is pure greedy exploitation. You are maximizing your expected reward based solely on your current, severely limited pool of knowledge.
But the research is very clear that pure greedy exploitation leads to fatal, suboptimal traps.
Fatal traps.
If I only ever stick to what I know works okay, I might be completely missing out on a massive life-changing jackpot on the machine right next to me, simply because I never bothered to put a single coin in it to try it out.
You are confusing your local success for global perfection.
Precisely.
And if your knowledge of the environment is incomplete, which it almost always is, your current best option might be objectively terrible in the grand scheme of the universe.
So how does the math solve this?
You must introduce a mathematical mechanism for boundary probing. You must proactively choose to explore in order to correct your own prior assumptions.
It must seek out falsification.
Exactly. And this is elegantly captured in a highly specific action selection formula called the upper confidence bound, or UCB.
Okay, let's unpack this.
Right.
Now, I don't want to just read out the raw algebra of the UCB formula, because listening to math is like trying to eat soup with a fork.
It really is.
But I want to break down its conceptual geometry, because it tells a profoundly human story. The formula essentially balances two competing forces on a scale, right?
It absolutely does. Let's dissect the two sides of this mathematical scale. On one side, you have the pure greed component.
The exploitation.
Right. This is the algorithm looking at its internal historical ledger and saying, historically, action A has given me an average reward of 10, and action B has given me an average reward of 5. I want the 10. I am going to exploit.
And if we only build our AI with this side of the scale,
the algorithm would instantly collapse into a local optimum. The very first time it found something mildly rewarding, it would become completely rigid and never learn anything new for the rest of eternity.
this is the classic restaurant dilemma.
Oh, I like this one.
Think about your own life, or anyone listening to this. You have your favorite restaurant. Let's say it's a cozy local Italian place down the street.
You know the garlic bread is good.
You know it's good. You've been there 20 times. You know the pasta is a solid 8 out of 10. That is your high, established historical value.
Your greed baseline.
Exactly.
Yeah.
But there's a brand new sushi place that just opened directly across the street. You have never been there. Its value is completely unknown to you.
It could be terrible.
It could be a 0, or it could be a Michelin star 10 out of 10.
Yeah.
If your brain operates purely on algorithmic greed, you will go to the Italian place every single Friday night for the rest of your life.
You will take the guaranteed 8 over the unknown.
You will never ever discover if the sushi place is a 10.
Which brings us to the other side of the scale in the UCB framework, This is the mathematical engine of curiosity.
How does that engine work?
It doesn't measure reward. It measures uncertainty. It measures the variance in your knowledge about a specific action.
Interesting.
This side of the equation has two massive drivers. First, it tracks the sheer passage of time. As time ticks forward, this uncertainty engine slowly but constantly grows in power. It generates a growing psychological pressure.
Like FOMO, fear of missing out.
Exactly like algorithmic FOMO. Second, it tracks exactly how many times you have actually tried a specific action. The more you try an action, the more you shrink the uncertainty engine for that specific choice.
Oh, this is brilliant. So let's map that back to the restaurants. If you keep going to the Italian restaurant week after week, your familiarity with it gets huge.
Right.
You shrink the whole curiosity pressure down to absolute zero for that specific Italian place.
Yeah.
You are extremely confident about
But
it.
for the sushi place across the street,
You've still never been. Your familiarity is zero. Meanwhile, time is relentlessly marching on, week after week, Friday after Friday.
the sheer passage of time is inflating the uncertainty bonus for the sushi place.
Exactly. The mathematical tension slowly builds until it reaches an absolute breaking point.
It does.
Eventually, the artificially inflated uncertainty bonus for the unvisited sushi place becomes so massive that it tips the scales. It mathematically overwhelms the known, guaranteed reward of the Italian place.
The algorithm is literally forced by the passage of time to go try the new restaurant.
It cannot help itself. The math absolutely demands exploration to prevent behavioral collapse.
And the beauty is there is a tiny variable in this formula, a confidence parameter, that acts like a volume knob.
A volume knob for curiosity.
Yes, you can turn it up to make the AI incredibly adventurous and reckless, or turn it down to make it highly conservative and stubborn.
I love how you phrase that. The math demands exploration to prevent behavioral collapse. Another analogy that comes to mind is the energy sector.
Okay, let's hear it.
Think about deep-sea oil drilling. An energy conglomerate has a known, established well that is pumping out a steady, highly profitable stream of crude oil.
That is pure exploitation.
Right. But they take a massive portion of those guaranteed profits and voluntarily set them on fire to fund an expedition to explore a new, potentially massive but highly uncertain reservoir in a totally unexplored trench.
Because if they don't, they eventually run out of oil.
Exactly. The UCB logic mathematically optimizes exactly how much capital you should spend pumping the known well versus how much you should risk drilling into the terrifying unknown.
Based purely on how long your company has been operating and how many times you've surveyed the new site.
It's breathtaking how a few variables capture that universal tension of survival.
It is the algorithmic formalization of the scientific method itself, hard-coded right into the action selection cortex of the agent. You have a hypothesis about the world that the Italian place is the best food in town.
But to be a rigorous scientist, you cannot just repeatedly confirm your own bias.
You must actively, deliberately seek out areas of high uncertainty to gather new data and attempt to falsify your own assumptions.
Okay, here's where it gets really interesting, though. We just spent all this time talking about navigating total, terrifying uncertainty. But let's flip the script entirely.
Let's do it.
The text moves on to explore a domain where the fog of war is lifted. What happens to the math when the system actually knows everything?
It's the God's eye view.
Yes, when we have absolute, perfect, crystalline information. The physics, the rules, the entire probability engine of the universe is fully mapped out and handed to the AI on a silver platter.
The literature refers to this domain as dynamic programming.
Dynamic programming. Okay, let's unpack this.
Dynamic programming, or DP, represents the theoretical ceiling of what is computationally possible. It is the realm of perfect logic.
Because there's no more guessing.
Right. If you possess the complete transition dynamics of the universe you inhabit, meaning you know exactly what every single action will do in every single state with absolute probabilistic certainty, you don't actually need to physically explore the world through trial and error.
You don't need to risk drilling the dry oil well.
You can compute the perfect, flawless path through the universe using pure internal logical deduction. And the anchor point for this entire realm of computation is the Bellman optimality equation.
Now, I'm looking at the sections breaking down the Bellman equation, and my eyes are crossing a bit.
It's notoriously tricky at first glance.
Because it looks like a paradox.
Yeah.
It looks like a loop. It essentially says that the optimal value of your current state is defined by the maximum reward you can get right now, plus the optimal value of the next state you are going to land in.
That's the recursive nature of it.
It defines the ultimate truth of the universe by constantly referencing itself.
Wait, how does an algorithm actually untangle a self-referencing infinite loop to find a concrete answer? It's a great question.
If the definition of A requires B and the definition of B requires A, how do you even start?
That is the crux of the computational challenge. And the text resolves it through a breathtaking process called generalized policy iteration, or GPI.
GPI.
GPI is an eternal, rigorous mathematical dance between two opposing but entirely complementary forces within the AI's mind: policy evaluation and policy improvement.
Okay, let's break that loop.
Imagine the algorithm is dropped into this perfect universe, but it starts with a completely random, objectively terrible strategy for how to behave.
Just totally clueless.
First, it triggers policy evaluation. It uses its God's eye view of the rules to sweep through every single possible state in the universe and calculate exactly how catastrophic its current strategy is.
It asks itself, if I rigidly follow my current dumb rules to the end of time, what is my precise expected payoff from every single location?
Exactly. So it's not trying to get better yet.
It's just brutally, honestly finding the mathematical truth of its current flawed existence.
It establishes an unvarnished baseline of reality. It calculates the true value of its bad habits. Once that evaluation process converges and the AI knows exactly how bad its strategy is, the system instantly shifts gears into policy improvement.
Okay, the second step.
It looks at the massive landscape of values it just painstakingly calculated, and it has an epiphany. It says, wait a minute, in state X, my current dumb rulebook tells me to go left, which I now know eventually leads to a miserable value of 5.
Right.
But because I have the God's eye model of the physics, I can see that if I simply changed my mind and went right instead, I would immediately land in a state that I just calculated has a value of 100. Therefore, I am throwing away the old rulebook. I will instantly rewrite my neural pathways. From now on, in state X, I go right.
It makes its strategy completely greedy with respect to the freshly calculated truths.
But wait, I see the trap here.
Do you?
Yeah, because the AI just drastically changed its strategy to be better, all of those baseline values it just spent so much time calculating the first step are now completely wrong. Exactly. The future has changed.
So it has to throw those values out,
Yep.
go back to policy evaluation, and calculate the true new value of this new, slightly less terrible strategy.
And then the cycle just repeats.
Evaluation, improvement, evaluation, improvement. It's a pendulum.
You've grasped the exact mechanics of the pendulum. And what is profoundly beautiful about generalized policy iteration is that the underlying mathematics identify this process as a strict compression mapping in a metric space.
Okay, hold on. Compression mapping in a metric space. You're going to have to translate that into plain English for me before we move on.
Sure enough.
What does that actually mean for the AI?
Apologies, it is a dense term from functional analysis. In plain English, it is an absolute mathematical guarantee of salvation.
Salvation.
It means that every single time you swing that pendulum, every time you run this dual process of evaluation and improvement, the mathematical distance between your current flawed strategy and the absolute global truth of the universe, the optimal policy must shrink.
It is physically impossible for the strategy to get worse.
It is trapped in a contracting space. It must inexorably, inevitably converge onto the single, perfect, mathematically optimal way to exist in that environment.
And once it hits perfection,
The pendulum stops swinging. Evaluation and improvement agree perfectly.
that makes so much sense. Think of a chess grandmaster, a true world champion who has completely memorized the rules of the game and the theoretical value of every piece configuration.
They don't need to touch the board.
Right. When they're staring at the board in a crucial, high-stakes endgame, they aren't physically moving pieces around on the wood to see what happens. They aren't doing trial and error.
They are running dynamic programming inside their biological neural net.
Exactly. They evaluate a potential sequence of moves, realize it leaves their king slightly exposed. They improve the policy by discarding that sequence. They evaluate a new line of attack
And they iterate this internal silent loop 1,000 times a minute.
until they find the one sequence that mathematically guarantees checkmate. They are sweeping the state space internally.
A magnificent analogy. The biological brain is simulating the Markov dynamics perfectly. My second analogy for GPI is a bit more artistic.
I'm intrigued.
It's like the process of editing a novel. You write a rough draft. That is your initial, highly flawed policy. Then you sit down and you read it carefully, evaluating every single sentence for rhythm, grammar, and emotional impact.
That reading phase is policy evaluation. You are determining the true value of the current text.
Exactly. Then you pick up a red pen and you cross out the clunky sentences and rewrite them to be sharper. That is policy improvement. You are acting greedily to maximize the literary quality based on your evaluation.
But then you have to read the new draft all over again, because changing the pacing of Chapter 2 might have completely ruined the emotional payoff of Chapter 3.
You evaluate, you improve over and over. The draft undergoes a compression mapping toward a final, published masterpiece where no further edits can improve it.
But there is a massive catch to all this elegance, isn't there? And this is where we have to pivot hard back to reality.
There's always a catch.
Dynamic programming requires that God's eye view. It requires you to hold the entire blueprint of the universe in your head.
Which is almost never the case.
Most of the time, in the real world, whether you are a robot or a human, we do not have a perfect model of physics. We don't know the precise probability distributions of the stock market, or the weather, or human traffic.
We are blind and we just have raw, messy, empirical experience.
To deal with this chaotic reality, the text introduces a whole new paradigm. Monte Carlo methods. Okay, let's unpack this.
Monte Carlo methods represent a massive philosophical and mathematical paradigm shift. We are completely abandoning the clean, deductive logic of dynamic programming.
And we are violently embracing raw inductive reasoning.
If you do not have the internal model to compute the truth in your head, you must discover the truth through objective, undeniable, empirical evidence.
You have to literally live through full trajectories.
You have to undergo complete episodes of interaction with the world, from the very start to the absolute finish line, and then tally up the actual physical rewards you received along the way.
It's the difference between looking at the architectural blueprints of a maze to find the exit versus just dropping a rat into the physical maze 10,000 times and using a stopwatch to track where it goes.
That's precisely it. Monte Carlo strips away the need for an internal model entirely.
It uses absolute, undeniable reality to falsify the agent's subjective internal assumptions.
If the AI thinks taking a certain highway is the fastest route, but after driving it 100 times in a Monte Carlo simulation, that route consistently leads to a 2-hour traffic jam.
The objective reality permanently overrides the subjective assumption.
And this reliance on raw experience introduces a profound algorithmic challenge. The text addresses this through a complex mathematical concept called off-policy importance sampling, denoted by the Greek letter rho.
Right.
The core problem is this. If you are an AI learning purely from experiencing the world, how do you learn about an optimal, highly efficient, brilliant strategy if the behavior you are currently using to safely gather data is completely random, chaotic, or overly cautious?
How does an AI learn the absolute best way to act? By observing someone else's heavily flawed behavior.
Exactly.
This is such a critical question, and I want to spend some time here. The text provides a formula for this important sampling ratio. It's a product of ratios looking at the probability of taking an action under your target policy, divided by the probability of taking that exact same action under the behavior policy that actually generated the data.
It's mathematically dense.
But reading probabilities over the airwaves is tough.
Yeah.
Let's make this tangible. How does this mathematical ratio actually function as a filter?
Let's use an extreme driving analogy. Imagine you are a highly advanced AI trying to learn the perfectly optimal, mathematically safest, and fastest way to drive a Formula One race car around a track.
Okay.
That perfect driving style is your target policy. But for safety reasons, you are not allowed to actually touch the steering wheel yet. You are sitting shotgun, passively observing a human driver.
I'm in the passenger seat.
But this human driver is wild. They are unpredictable, they are angry, and they take corners far too aggressively. That human's chaotic driving style is your behavior policy, the source generating your raw data.
Right. So as the AI, I am experiencing the physics of the track. I'm seeing the curves, feeling the G-forces, mapping the straightaways.
Yes.
But I am experiencing all of that crucial reality through the heavily distorted lens of a crazy driver. If I just naively recorded and copied everything that happened, I wouldn't learn to be an optimal driver. I would just learn to be a crazy driver.
Exactly. You would inherit all of their flaws. So you must mathematically filter out their crazy biases on the fly to improve your own safe strategy.
And this is exactly what the important sampling ratio does.
Every single time the wild driver approaches a corner and violently jerks the wheel, the AI's internal math asks a targeted question. What was the probability that the perfectly optimal safe policy I'm trying to become would have taken that exact same violent action? If the crazy driver drifts wildly into the grass and your optimal policy dictates you would never, ever do that, the target probability in the numerator of your ratio drops to 0.
The entire mathematical fraction becomes 0.
The mathematical filter instantly kills that specific data point. It tells the AI's memory bank, do not learn from this specific second of data. It is completely irrelevant to my goals.
But let's say a broken clock is right twice a day. What if the wild driver, purely by accident, happens to perfectly hit the apex of a hairpin turn, braking at the exact optimal millisecond, executing the turn exactly the way the AI's optimal target policy would want to?
Then the magic of the ratio kicks in. Because the crazy driver did exactly what the perfect policy would do. The ratio of the target probability over the behavior probability spikes.
The filter actually mathematically amplifies that specific data point.
It screams at the AI's memory. Yes, pay massive attention to this. Even though a chaotic person did this specific subsequence of actions perfectly aligns with ultimate perfection. Extract the value from this moment and learn deeply from it.
It is constantly dynamically adjusting the statistical weight of the experience based on how closely it matches the ideal.
Exactly.
What's fascinating here is that importance sampling isn't just a neat trick for autonomous cars. It acts as a foundational mathematical bridge that allows knowledge to migrate safely across entirely different probability spaces.
Absolutely.
My favorite real-world application for this concept is in large-scale medical trials. Let's say a pharmaceutical company is testing a revolutionary new drug, and they test it on a control group of 1,000 volunteers.
Right.
But because of how recruiting works, those volunteers happen to be mostly healthy, 20-year-old college students. That specific demographic distribution is your behavior policy, the source generating the clinical data.
But your target policy, the real-world application, is the entire global population, which includes the elderly, toddlers, and people with compromised immune systems.
You cannot simply take the raw, unfiltered success rate from a room full of 20-year-olds and blindly extrapolate it to an 80-year-old patient. The raw data is fundamentally biased by the source distribution. If you do that, people will die.
Precisely. You have to use importance sampling. The statisticians look at the metabolic results from a 20-year-old healthy male in the trial, and they mathematically downweight that specific data point's influence when trying to predict the drug's effect on an 80-year-old woman.
Because the probabilities of those two biological demographics matching are drastically different.
Importance sampling is the rigorous, uncompromising mathematical mechanism that allows an algorithm or a human scientist to say, I am forced to observe reality from a highly biased vantage point, but I have the tools to perfectly extract the unbiased universal truth from it.
That is a brilliant translation of the mathematics into human stakes. But while Monte Carlo and importance sampling are powerful, the literature is very clear about a massive, crippling limitation of these methods.
The weighting problem.
Yes. And this brings us to a major evolutionary leap in the math: temporal difference learning, or TD learning. The fatal flaw with Monte Carlo is that you have to wait until the absolute bitter end of an episode to learn a single thing.
Which is terribly inefficient.
If you are using Monte Carlo to learn how to play a game of chess, you have to play the entire game, endure all 80 moves, wait for the king to be captured, and only then can you go back and retroactively adjust the values of the moves you made an hour ago. That is agonizingly, painfully slow.
It is incredibly computationally inefficient to wait for terminal states. Imagine a human trying to navigate life that way.
It would be impossible. If you're a toddler and you start walking into a busy street, you wouldn't learn that it was a dangerous idea until you actually got hit by a car at the end of the episode.
You would have to die to learn.
We desperately need a system that learns instantly, on the fly, mid-stride. And that is exactly what temporal difference learning provides. The text presents TD learning as the ultimate holy grail hybrid.
It takes the objective reality sampling of Monte Carlo and violently fuses it with the rapid, step-by-step updating of dynamic programming.
The authors refer to this as the metacognition of TD, which relies on a deeply profound concept called bootstrapping. Bootstrapping is essentially the mathematical act of guessing based on a guess, but doing so in a way that is rigorously anchored to reality.
Right.
Now, I always struggle with that concept. Guessing based on a guess sounds like a recipe for a hallucination. How does that actually create reliable learning?
It works because of the injection of micro-reality. In TD learning, you are constantly updating your current subjective estimate of a state's value based on the estimated value of the very next state you step into, plus the immediate physical reward you just received.
You do not wait for the end of time.
The mathematical heartbeat of this entire process is a tiny, beautiful variable called the TD error. denoted by the lowercase delta.
Let's focus entirely on that delta. The text frames the TD error as the mathematical equivalent of surprise or falsification.
That is exactly what it is. Imagine the equation. You have your old guess, what you expected the value of your current situation to be based on your past experience.
Right.
Then you take one single step forward in time. You observe a tiny slice of reality, the immediate reward you get for taking that step. You add that tiny slice of absolute reality to your guess about the next state.
This creates a new, slightly more informed guess.
The TD error is simply the mathematical difference between your old, ignorant guess and your new, slightly more realistic guess.
So if the error is exactly 0,
It means your expectation perfectly matched reality. You are perfectly right. You experience zero surprise, and therefore no learning is required. Your neural weights stay exactly the same.
but if the error is a positive number, it means the world just handed you a better outcome than your internal model predicted. It was a pleasant surprise, a hit of dopamine.
And if the error is negative, reality was worse than you thought and you were disappointed.
The TD error is the constant, streaming heartbeat of learning, adjusting the system's internal synapses millisecond by millisecond as it moves through time.
Think about the daily human struggle of predicting the weather.
Oh, this is a good one.
If I am using a Monte Carlo approach, I have to make a grand prediction on January 1st about exactly what the weather will be on December 31st. And I absolutely cannot check my accuracy, adjust my models, or learn from my mistakes until the very last second of the year.
That is an absurd way to run a meteorological institute.
TD learning is like making a localized prediction on Monday about what Tuesday will be like. On Tuesday morning, I walk outside, I experience the real physical weather. I measure my surprise, my TD error between what I predicted and what I feel.
You instantly update your weather predicting model.
And then I use that smarter model to make a prediction for Wednesday. I am constantly bootstrapping my way through time, riding the wave of the present moment.
A fantastic, grounded analogy. Now, the text dives exhaustively into the two main evolutionary branches of TD control,
Yeah.
SARSA and Q learning. I want to spend a significant amount of time focusing heavily on Q learning, because it is rightfully highlighted by historians of computer science as a monumental milestone in artificial intelligence.
It truly was a breakthrough.
It was the breakthrough that made a massive portion of modern autonomous AI even possible.
It is a profound algorithm. The literature emphasizes the introduction of a specific mathematical operator in the Q-learning update rule, the max operator.
The max operator.
This single operator changes the entire geometry of how the AI views the future. What Q-learning does is violently decouple the act of learning from the act of behavior.
We just talked about importance sampling being a complex, fragile way to learn off policy.
Q-learning achieves off-policy learning without complex probability ratios. It does something violently elegant and incredibly aggressive.
How so? What is so aggressive about the max operator?
Regardless of what chaotic, exploratory, or downright foolish action you actually took to physically stumble into the next state, the Q-learning update rule stops, looks at that next state, and says, I am going to completely ignore what the behavior policy is planning to do next.
Okay.
Instead, I am going to mathematically assume that from this exact state forward until the end of time, I will act with absolute, flawless perfection. I will sweep across all possible actions available in this next state, and I will strictly extract the maximum possible value.
Wow. It's an aggressive, unbreakable assumption of future perfection. Even if the agent is currently acting like a drunken sailor to explore the map, its internal learning mechanism is assuming it will suddenly become a flawless genius on the very next step.
Yes. It forces the internal estimated values to rapidly, aggressively converge on the absolute global optimum, regardless of how exploratory the physical body of the agent is acting.
I love this.
Imagine you are in a small boat in the middle of a violent, unpredictable ocean storm. You are being tossed around randomly by the non-stationary waves of exploratory data streams. You have no control over your immediate trajectory.
But you have fired a titanium grappling hook that has anchored your boat directly to a massive, immovable lighthouse on the distant shore.
That lighthouse is the global optimum represented by the max operator. No matter how wildly you are thrown around by the waves of your own exploratory behavior, that mathematical anchor pulls your internal value system relentlessly, inexorably toward the absolute truth.
You can explore the ocean wildly, but you are learning the perfect path to the shore perfectly.
That is an incredible visualization.
So we've established how to learn instantly on the fly and how to anchor ourselves to perfection. But what does this all mean for the deep, long-term memory of the system?
Ah, the memory problem.
This brings us to a massive conceptual hurdle in the field, moving into the concept of eligibility traces. I absolutely love the setup for this because it gets to the absolute core of how tricky causality is in our universe.
It's one of the hardest problems in physics and philosophy.
Let me ask you, the listener, a direct question. Imagine you're playing a grueling, intense, 3-hour game of chess against a master. On move 80, you finally deliver a crushing checkmate and win the game. The dopamine hits.
Was it the very last move that actually won you the game?
Right. Or was it that brilliant, incredibly subtle pawn sacrifice you made on move 22 hours ago that invisibly dismantled your opponent's long-term defense?
This specific paradox is universally known in the field of AI as the credit assignment problem. And it is a massive, debilitating computational headache.
When a massively delayed reward finally arrives, like winning the game of chess hours after it started, how does the algorithm accurately distribute the credit or the blame backward through the incredibly long, complex chain of millions of microscopic decisions that led to that exact moment?
Standard temporal difference learning, which we just praised, only looks one single step ahead. It struggles violently with deep causal chains because it is too nearsighted. Standard Monte Carlo, on the other hand, which looks at the whole episode, takes the final reward and essentially smears it equally across every single move you made, which is highly inaccurate.
Right. If you win the chess game, Monte Carlo sweeps through and says, every single move you made was a stroke of absolute genius. Even that objectively dumb mistake you made on move 5 that almost cost you your queen. It's far too blunt of an instrument. It lacks nuance.
Precisely. The text outlines the ultimate mathematical solution to this problem, the folding of causal chains through a mechanism called eligibility traces, specifically formalized as an algorithm called TD lambda.
TD lambda.
This is where the mathematics perform a literal sort of computational time travel. It transforms what theorists call a forward view, where an algorithm theoretically has to wait endlessly for future events to actually happen in order to update the present, into a computationally brilliant backward view.
In the backward view, the algorithm instantly, efficiently updates the distant past, based purely on the reality of the present moment.
The core tuning variable here is lambda. The text describes lambda as a sliding scale, a continuum stretching from a value of 0 to 1.
If we set lambda to exactly 0, we lobotomize the deep memory. We're doing pure, single-step TD learning, just staring right at the tips of our toes.
And if we set lambda to exactly 1, we are doing pure Monte Carlo, waiting for the end of time to judge anything.
But if we set lambda somewhere in the middle, say 0.9, we unlock absolute magic. We create an eligibility trace vector.
Let's paint a picture of how this decaying memory buffer actually works in physical space.
Yes, please.
I like to visualize this vector as a mathematical ledger of recent physical activity, but one that is constantly evaporating. Imagine you are walking through a massive, pitch-black forest. Every single time you take a step into a new clearing, a new state, you leave a glowing, radioactive footprint on the ground.
The moment your foot leaves the ground, the footprint is blazing with bright light.
That state is now highly eligible to learn from whatever happens next. But as you continue walking away, the glow of that footprint isn't permanent. On every subsequent millisecond, the mathematical brightness of that footprint decays, multiplied by our discount factor gamma and our trace parameter lambda.
The light slowly, inevitably fades into the dark.
I can picture that perfectly. You keep walking, twisting and turning through the dark forest, leaving a long, winding trail of footprints behind you. The most recent steps right behind you are still blazing bright neon, but the steps from an hour ago at the edge of the forest are just a barely visible, dim glimmer.
And then, suddenly, you stumble into a clearing and find a massive treasure chest. A massive, unexpected, positive TD error hits your system. What mechanically happens to the trail?
This is where the backward view time travel happens. When that massive TD error hits, the system doesn't just statically update the value of the dirt you are currently standing on. It takes that massive positive signal and it violently broadcasts it backward along the entire historical eligibility trace vector.
Every single state in the forest that still has a non-zero glowing footprint gets a portion of the treasure's reward.
But the distribution is perfectly geometrically fair. The states with the brightest footprints, the actions you took just seconds ago, get a massive share of the credit because mathematically they were most directly, causally responsible for leading you to the treasure.
The dim, fading footprints from an hour ago get a tiny, microscopic fractional update. The trace perfectly, organically aligns the strength of the learning update with the recency and the frequency of the past actions.
It is an incredibly elegant, fair way to solve credit assignment.
Think about a massive corporate bonus structure. A massive enterprise software deal closes today for $10 million. Who gets the massive commission check?
The salesperson who physically got the signature on the dotted line today gets a large cut.
But what about the marketing team who pitched the initial brilliant ad campaign 6 months ago that brought the client in? They should absolutely get a cut too, but a proportionally smaller one.
What about the product engineers who built the custom demo 3 months ago? They get a cut.
The eligibility trace is a perfect corporate accountant. It mathematically tracks all of those historical contributions, geometrically decaying their weight over time, and perfectly distributes the final reward backward upon closing.
And computationally, geometrically, it allows for highly efficient parallel processing across the axis of time. You are simultaneously updating a vast, sprawling history of thousands of states on every single microscopic time step without having to maintain a perfect, distinct, memory-heavy record of every single prior moment.
That single, elegant vector compresses the entire causal history of the universe into a highly usable gradient.
Okay, let's take a deep breath.
Yeah, because we are about to pivot into a section of the literature that crosses from pure mathematical calculation into something that almost sounds like science fiction.
The dreaming AI.
Exactly. We are moving into the domain of the Dyna architecture and the concept of planning. Essentially, we're introducing the mathematical framework for an AI that dreams or hallucinates in order to get smarter, faster, without moving a muscle.
This represents a profound architectural leap in the evolution of artificial intelligence. Up until this point in our deep dive, we have treated learning and planning as two totally distinct, isolated modes of existence.
Right. You either learn blindly from brutal physical experience using TD or Monte Carlo, or you sit in a room and plan using perfect divine knowledge of the rules using dynamic programming.
Dyna shatters that wall. It unites them into a brilliantly efficient dual-track evolution system. It is born from the pragmatic realization that physical interaction with reality is incredibly expensive, painfully slow, and sometimes fatally dangerous.
Absolutely. You can't take a physical $1 million autonomous prototype car and crash it into a wall 10,000 times just to let the algorithm learn how to parallel park. The physical cost is impossible.
Exactly. So, the Dyna architecture proposes a parallel schizophrenic structure for the AI's mind.
Track 1 is anchored in reality. The agent takes a physical action in the real world, observes the real physical consequence, and updates its value network using standard, model-free reinforcement learning.
But crucially, secretly, it takes that exact same piece of real-world data and it routes a copy of it to train an internal model of the environment.
It slowly, painstakingly builds a virtual replica of the universe's physics inside its own silicon memory.
And once it has built this virtual simulated world inside its head, what does it actually do with it?
It hallucinates. It actively dreams.
Even the physical downtime and the idle microseconds between taking actual real-world actions while its physical servos are moving, the agent's brain completely disconnects from physical reality.
It drops fully into its internal virtual model and starts running simulated trajectories at lightning speed.
It picks a state it has visited before in the real world, it picks an action, and it asks its internal simulation, what would happen if I did this right now? The internal model, based on past data, spits out a simulated next state and a fake simulated reward.
The agent then applies its exact learning algorithms to this fake data as if it were absolute reality.
It's running simulated annealing on its own imagination. It is generating synthetic experience to train itself.
Yes, my absolute favorite analogy for this is an elite Olympic downhill skier. Picture them standing at the starting gate at the top of the mountain. The physical race hasn't started yet. They're perfectly still.
But they have their eyes closed, their breathing is controlled, and if you look closely, their body is micro-twitching.
They are running a high-frequency internal simulation of the entire 3-minute slalom course. They are anticipating the sharp turns, visualizing the icy patches, bracing for the jumps, entirely based on their mental model of the mountain from their practice runs.
They are heavily updating their neural value pathways and muscle memory before they ever push off the gate. That is exactly, mathematically, what Dyna is doing computationally in the background.
Or think about a massive, multi-billion-dollar global logistics business. They don't just sit around and wait to see what happens when the global markets open.
They run thousands of hyper-complex supply chain simulations overnight on their server farms.
What if a Category 5 hurricane hits the Atlantic shipping lanes? What if jet fuel prices spike by 20%? What if a supplier goes bankrupt?
They generate endless streams of simulated catastrophic experience to stress test and prepare their logistical policies for tomorrow's chaotic reality. It accelerates the convergence of their strategy astronomically because simulated, hallucinated experience in a computer is infinitely cheaper than real-world failure.
That is exactly the commercial application. And the text highlights a highly critical, brilliant extension of this architecture known as DynaQ+.
If we connect this hallucination engine back to the bigger picture of non-stationary environments, worlds that are constantly shifting and changing, a major, potentially fatal problem arises when reality changes behind the agent's back.
What if our AI has learned the perfectly optimal path through a physical maze, but while it was asleep, a wall collapsed and a massive new shortcut opened up?
The agent's internal model still aggressively insists that the shortcut is a solid, impenetrable wall. It will never ever try to go down that path because its model says it's impossible. It is busy perfectly exploiting the known longer path.
It becomes entirely trapped by its own outdated assumptions. It's living in the past. How does the math of DynaQ+ fix a psychological block like that?
It mathematically, violently forces skepticism into the AI's dreams. DynaQ+ introduces a timer. It meticulously tracks exactly how much time has passed since the agent last physically visited every single state in the real world.
When the agent goes to sleep and hallucinates in its internal model, it doesn't just use the standard expected reward. It artificially injects a massive reward bonus into the simulation for states that haven't been visited in a long time.
The math literally inflates the value of the unknown based on the square root of the elapsed time.
Oh, that is incredibly clever. The longer it ignores a specific corner of the real world, the more its own imagination warps to make that corner look incredibly, irresistibly appealing.
It mathematically compels the agent to break its perfectly established, highly efficient routine, physically drive out into the world, and test that ignored, dusty corner just to see if the physics have changed.
It prevents the internal model from permanently desyncing from a shifting physical reality.
It is the flawless, algorithmic instantiation of human curiosity, driven entirely by the relentless passage of time. But as brilliant and elegant as Dyna and these tabular methods are, the literature warns us that they operate on a fundamentally flawed, doomed premise if we ever want to scale AI to true, real-world complexity.
And that brings us face to face with the computational apocalypse, the combinatorial explosion.
Right. Let's tackle this head on. Up to this point in our discussion, we have been implicitly, quietly assuming that the AI is capable of keeping a perfect, tidy little Excel spreadsheet, a table of every single possible state in the universe, and every single possible action it could take.
But what happens when the universe is simply too big? Think about the ancient board game of Go. The text explicitly mentions that the number of possible legal board states in Go is vastly greater than the number of physical atoms in the observable universe.
You simply cannot build a physical spreadsheet with more rows than there are atoms. The physical silicon memory required to store that table would literally collapse under its own mass into a black hole.
This is the terrifying threshold where we must completely abandon the comfort of exact mathematical certainty. We have to make a terrifying leap into abstraction. We must discard the discrete, perfect tabular mappings, and we must turn to function approximation.
Specifically, the integration of deep neural networks. We have to completely stop trying to memorize the exact perfect value of every single specific state, and instead we try to construct a parameterized, low-dimensional mathematical manifold that roughly approximates the high-dimensional truth.
We are taking the infinite complexity of the universe and violently compressing it into a small set of neural weights. Now, the text introduces the objective function for this, the mean squared value error.
Without reading the algebra, let's unpack what this equation is actually trying to accomplish psychologically for the AI.
It is defining the strict geometry of compromise. The AI now fundamentally knows that it cannot be perfectly accurate everywhere. It doesn't have the memory.
So this formula calculates the mathematical distance between the true, God-given value of a state in reality and the neural network's current blurry guess. It takes that error and it squares it, which mathematically punishes large, catastrophic deviations much more severely than tiny mistakes.
And crucially, it weights the error by how often the AI actually visits that state. The system's entire architectural goal is to use calculus to dynamically adjust its parameter weights to make this global sum of errors across the entire universe as close to zero as theoretically possible.
And it drives this optimization using the absolute engine of modern AI, stochastic gradient descent. The AI calculates the gradient, which acts as a multidimensional mathematical compass.
It tells the millions of neural weights exactly which direction to shift, by a microscopic fraction to slide down the slope of error toward truth.
What is truly revolutionary here, what changes the entire nature of machine intelligence, is the concept of generalization. In our old tabular system, learning that state A is bad tells the AI absolutely, strictly nothing about state B. They are isolated islands of data.
But with a neural network, states are no longer distinct. They are represented by overlapping feature vectors. If the system learns that a state possessing feature X is highly rewarding, the gradient descent update alters the neural weights in a way that automatically, instantly increases the estimated value of every other unseen state in the universe that shares feature X.
This is exactly precisely how human cognition works. Think about it. You, as a human, do not need to memorize the exact face and dimensions of every single individual dog on planet Earth to know what a dog is. You don't have the memory capacity for that.
Instead, your brain learns the generalized features fur, a specific type of acoustic bark, a wet snout. The very first time you see a rare breed you've never ever encountered before, like a borzoi, your brain doesn't crash.
You don't output a blue screen of death. You look at the features, you run them through your biological neural net, your brain generalizes from decades of past experience, and you instantly output the correct classification. Dog.
The mathematical leap from discrete tables to function approximation is the exact defining moment. Computational memory transforms into true abstract reasoning.
Another beautiful way to visualize this geometric compression is drawing a line of best fit through a massive, chaotic scatter plot of data points. Imagine you have a graph with 50 million messy, scattered dots representing raw, real-world experience.
You cannot possibly memorize the x and y coordinates of where every single dot is. But using calculus, you can calculate the slope and intercept of a single straight line requiring just 2 parameters of memory that perfectly captures the fundamental underlying trend of the entire massive cloud of data.
The deep neural network is just doing that exact same process, but with billions of parameters twisting and bending a hyperplane through a multidimensional space.
But the text immediately hits us with a massive, terrifying warning sign right after introducing this. The leap to abstract reasoning is not safe. In fact, it introduces a highly specific mathematical recipe for total, catastrophic algorithmic collapse.
The literature ominously calls it the deadly triad.
I want you, the listener, to pay incredibly close attention here, because this is the exact trap where modern billion-dollar AI training runs catch on fire and burn to the ground.
The deadly triad is one of the most famous, feared, and heavily studied phenomena in the entire field of reinforcement learning. The theorem brutally states that if you combine 3 specific, incredibly common AI techniques, absolute mathematical stability is no longer guaranteed, and the entire system can dynamically, explosively diverge to infinity.
The 3 toxic ingredients are, first, function approximation, which we just discussed using a deep neural network instead of a safe discrete table. Second, bootstrapping using TD learning, where you are constantly updating a guess based on another subjective guess. And third, off-policy learning, trying to learn about an optimal target policy while physically following a completely different chaotic behavior policy.
If you mix those 3 ingredients in a cauldron, boom. The text explicitly cites something called Baird's counterexample. I was reading this, and it is a beautifully simple, artificially constructed environment specifically designed by researchers to prove this exact mathematical nightmare.
In Baird's counterexample, an agent follows the deadly triad. But instead of learning the optimal path, its internal neural weights literally spiral out of control. They grow exponentially larger and larger on every step until the numbers hit the absolute physical limits of the computer's floating point memory architecture, and it outputs NaN, not a number.
The AI experiences a fatal, massive mathematical stroke. How does this actually happen geometrically?
The geometry of the failure is a fascinating, tragic study in feedback loops. Because you're bootstrapping, your AI is constantly chasing a moving target. It's updating its beliefs based on its own shifting beliefs.
Because you are off policy, the physical data distribution you are sampling from is severely, fundamentally mismatched with the theoretical target you are trying to learn about.
And critically, because you are using function approximation, A learning update in one specific state violently rips and distorts the values of all the other states around it due to the generalization feature we just praised.
The system enters a vicious, self-amplifying cycle of distortion.
It's like my favorite analogy for this. Audio feedback at a live rock concert. You have a microphone, which is the data intake, and a massive speaker, which is the value output. If the lead singer accidentally gets the microphone too close to the speaker, the microphone picks up a tiny microscopic bit of ambient background noise.
It feeds it into the amplifier, the speaker blasts that noise out slightly louder, the microphone instantly picks up the louder noise, amplifies it again.
And within 2 seconds, the entire system spirals into an infinite deafening screech that literally blows out the physical hardware. Baird's counterexample is the algorithmic mathematical equivalent of that stage screech.
It is exactly that. And to solve this screech, the literature details an absolute tour de force of advanced mathematics. The gradient TD family of algorithms, specifically highlighting a breakthrough called GTD2.
The fundamental genius realization by the researchers was that naive temporal difference learning, when strapped to a neural network, isn't actually following a true mathematical gradient.
It is taking dangerous geometric shortcuts that are fundamentally inherently unsafe when operating off policy.
So how does GTD2 fix the warped geometry? The text mentions that it minimizes something called the projected Bellman error, or PBE. Again, I don't want to read the raw formula because it is terrifyingly dense, but walk us through the conceptual space of the PBE.
Think of it this way. You are attempting to represent a highly complex, infinite-dimensional, godlike truth, the true Bellman equation of the universe, using a severely constrained, low-dimensional flat sheet of paper, which is your neural network.
The ultimate truth exists floating in the air, in high-dimensional space, high above your paper.
The core operator in the GTD2 equation is a geometric projection. Imagine shining a perfectly straight mathematical flashlight from straight above the floating truth, casting a flat 2D shadow directly onto your piece of paper. The projected Bellman error simply, elegantly measures how far your current neural network weights are from that specific shadow.
GTD2 forces the algorithm to rigorously, strictly follow the true gradient of that specific shadow, rather than blindly chasing the floating truth itself.
It mathematically prevents the distortion. Imagine you were trying to drive a car at highway speeds while looking entirely through a warped, twisted funhouse mirror. Everything is stretched, bent, and violently blown out of proportion.
If you try to steer the car based on that twisted reflection, which is what the deadly triad does, you will instantly violently crash into a wall.
GTD2 acts as a genius corrective lens. It projects the warped funhouse image back into a flat, safe, true geometric representation of reality, allowing you to steer your neural weights safely without diverging into infinity.
And mechanically, the way GTD2 achieves this mathematical stability is by introducing a second, separate set of weights. It operates on a brilliant 2-timescale system. One set of fast-moving weights acts as a scout, tracking the volatile TD error, while the main set of policy weights moves slowly, securely adjusting the core behavior.
This dual system architecture reestablishes the strict mathematical boundaries that guarantee the system will safely converge, even when operating entirely off policy with massively deep neural networks.
But all of this incredible effort to stabilize value estimation raises a profoundly important, almost heretical question in the field. We spent all this computation trying to perfectly estimate the value of states to figure out our behavior. But what if the whole concept of predicting value is just an unnecessary, bloated middleman?
Which brings us to the grand finale of this literature, the absolute summit of the mountain. We are throwing away the middleman entirely. We completely stop trying to predict how many arbitrary points a state is worth, and we directly, physically manipulate the topology of the system's brain to output actions. This is the domain of policy gradients.
Policy gradients represent a complete foundational paradigm shift in artificial intelligence. Instead of maintaining a massive, complex neural network that outputs a value estimate like Q-learning does, where it says going left is worth 10 points, we maintain a neural network that directly, explicitly outputs the mathematical probability of taking an action.
It says, there is a 90% chance you should go left. We parameterize the behavior itself. The ultimate goal is to directly perform mathematical gradient ascent on the performance objective by tweaking the network weights.
The text gives us the famous policy gradient theorem. It mathematically proves why we can do this. But conceptually, why is it so mathematically and practically superior to calculate the gradient of the probabilities directly, rather than relying on value estimates?
There are two profound, world-changing reasons. First, continuous action spaces. If you are an AI tasked with controlling a physical robotic arm in a factory, the joint angles aren't discrete, simple buttons like up, down, left, right on a keyboard. They are continuous, infinite fluid spectrums of torque and voltage.
A traditional Q-learning value table simply cannot handle infinite fractions of movement. The table would be infinitely large.
A policy gradient algorithm elegantly solves this. It simply outputs the mean and variance of a Gaussian probability distribution, smoothly and naturally controlling continuous physical momentum. Second, and perhaps more importantly, it solves imperfect information games.
Games where you don't know what the other person is holding, like poker.
Exactly. In high-stakes poker, if your AI plays deterministically, meaning if it always, 100% of the time, bluffs when it has a specific weak hand, a human opponent will figure out that pattern in 10 minutes and absolutely crush you.
To survive in poker or war or economics, you must be unpredictable. You must employ a stochastic policy where you deliberately choose to bluff exactly, say, 32.5% of the time.
Value-based methods like Q-learning naturally inevitably collapse into greedy, predictable, deterministic behavior. They struggle violently to maintain deliberate, calculated randomness. Policy gradients, however, mathematically and gracefully converge to the perfect, unexploitable stochastic probabilities required by advanced game theory.
And the absolute pinnacle architecture that utilizes this theorem is called the actor-critic system. This is the bedrock of the most advanced AI models on the planet today. The system literally violently splits its brain into two concurrent, arguing neural networks, the actor and the critic.
Let's look at the conceptual structure of the actor first. The actor is the executioner. It is the pure policy network. It looks at the world and decides what to do. The critic, on the other hand, is the evaluator.
It is a completely separate, isolated value network that sits back, passively watches what the actor physically does, calculates the TD error based on the reality of the reward, and uses that error as a brutal scalar baseline to judge the actor's performance.
I picture this as a stage actor rehearsing a highly emotional play, while an expert, highly critical, veteran director stands in the wings. The actor performs a scene on stage. They cry, they yell, they move across the floorboards. That is the physical execution of the policy.
The critic, the director, watches closely and immediately provides real-time harsh feedback. That was entirely too melodramatic. That represents a massive negative TD error. Or, the director yells, that was brilliant, exactly the subtle emotion we need. A massive positive TD error.
The actor takes that raw scalar critique and immediately instinctively adjusts their internal emotional mapping, tweaking their neural weights to perform slightly better on the next take. The actor doesn't need to know the complex physics of the stage lighting or the acoustics of the theater. They just need to relentlessly move their performance in the exact direction of the critic's applause.
Another powerful parallel is the structure of a modern publicly traded corporation. The CEO is the actor network. They are in the trenches making the day-to-day strategic decisions, signing contracts, launching experimental products, hiring and firing.
The board of directors is the critic network. The board isn't down on the factory floor physically building the product. They are completely abstracted from the execution. They are purely evaluating the financial trajectory of the company.
When the CEO makes a major strategic move, the board calculates the delta in the stock price and the projected quarterly revenue, the baseline TD error, and applies immense targeted pressure on the CEO to either continue pushing that strategy or to pivot immediately.
And when you mathematically combine this direct, fluid manipulation of probability, the actor, with the indirect, rigorous measurement of environmental value, the critic, you unlock absolute God-tier computation.
The source material concludes by stating that this exact indirect projection plus direct measurement union is the mathematical bedrock behind the most famous, world-altering AI triumphs in human history. Deep Blue dismantling Kasparov's legacy in chess. TD Gammon achieving terrifying superhuman backgammon play. And AlphaGo Zero completely dismantling the greatest human Go players on Earth in a game of pure intuition. They all rest on the foundation of these exact equations.
Because it is, quite simply, the most efficient known mathematical framework in the universe for synthesizing raw, chaotic physical experience into generalized, goal-directed, highly intelligent behavior, the intelligence doesn't need to be hard-coded by a programmer. It emerges inevitably, organically, from the rigorous, unyielding application of the gradients.
Which brings us to the wrap-up of this truly monumental deep dive. We have covered an astonishing, exhausting amount of intellectual ground today. We started at the absolute foundation. with the humble, discrete mathograph of a Markov decision process, defining the boundaries of states and actions.
We explored the multi-armed bandit, quantifying the exact agonizing mathematical tension between greedy exploitation and the necessary risk-taking curiosity of the upper confidence bound. We looked at the God's eye view of dynamic programming and how it inevitably converges on universal global truth through the pendulum swing of policy iteration.
We then stripped away that perfect divine model to embrace the messy, objective, falsifying filter of Monte Carlo importance sampling. We massively accelerated the math with the bootstrapping metacognition of temporal difference learning. We solved the deep, ancient mysteries of credit assignment by folding causal chains backward through the dimension of time using decaying eligibility traces.
We watched the AI actively dream and hallucinate its own simulated reality using the dual-track Dyna architecture. We survived the terrifying combinatorial explosion by leaping into the abstract, low-dimensional manifolds of deep neural networks, and we safely navigated the infinite divergence of the deadly triad using the brilliant geometric projections of GTD2.
Finally, we arrived at the summit, the actor-critic policy grid.